Okay, so here's our problem. And Ben Schreier, tell me what's your first step?
Um, don't we have to find I1 and I2? So, like get rid of like any direction or find our direction.
Okay, so your first thing you want to add your second direction. Is that what you're saying?
Yes, for
Okay,
I2.
so create your I1, I2. I'm going to suggest something to do even before you do that.
Um,
What kind of inputs do you have? Are
we
they
have
DC, DC steady? Are they DC steady state, step DC, AC, or something else?
steady state,
Some kind of steady state. Is it DC steady state or AC steady state?
DC.
It's not DC steady state because it's a function of time.
Oh, okay, then AC steady state.
So it's AC, sinusoidal steady state. So an example of a DC steady state input would be 20 volts. And it's always 20 volts and it's not changing. So that is DC steady state.
Oh, okay. Thank you. I actually was confused by that.
And then let's say we had a 20 volts times a U of T. Then that would be DC stepped because you're changing between two different values of DC. And then this is called sinusoidal steady state because it's a cosine wave. So if it's DC steady state, you'd use circuits one techniques. Capacitors are open, inductors are shorts, circuits one. Step DC, you use that method, those pre-chewed equations of the plug-and-check equations for first order or second order. And then if it's sinusoidal steady state, there's no U of T's here. There's nothing switching. It's been a sinusoid for an ever and ever. So any kind of initial conditions that were there have long since died away. That's when you use what method?
Mesh with the I1 and I2. That was asking.
That was the question, but that's not the answer. So every time we use sinusoidal state, just because there's a cosine here, we're not going to use mesh necessarily. We might, but we might use nodal or superposition or any of their circuits one techniques. Instead, when you see sinusoidal steady state, that means we're going to use the method of phasors. Just like if we're using DC steady state, that's when we'd use circuits one methods, capacitors are open, inductors are shorts. And if we're going to use step DC methods, that's when we use those pre-made plug-and-check equations that are valid for first and second order only. And then in our future class, we'll talk about how to use equations that work for any kind of source. And now we've got a cosine source, so we're going to use phasors. And so our first step is to convert them into the phasor domain. So Ben Wallace, tell me what is the voltage source here?
Yeah, is it
and Grant, you'll be on
10 to the square root of 2 with a degree of 45.
That's it.
Right there.
10 times square root of 2 at 45 degrees. And of course, resistors don't change. And how do we figure out what the impedance is of the inductor, Grant? Ruben, you'll be on next.
Do you use the equation J omega L?
That's it. So the impedance of an inductor is always equal to J omega L. So just continue on, Ruben. I'm sorry, just continue on, Grant. What's our omega?
You do omega, which is the 100.
That's right.
Times the 30 millihenries.
Times the 30 millihenries. So finishing up that, we get the number part is 3,000. And 1 times a milli is a milli. And that's all J. And what's the simpler way, Grant, of writing 3,000 millis?
Just 3.
Just J3. That's it. All right. And then we've got this capacitor. Ruben?
The impedance of the capacitor is 1 over J omega C. 1 over J omega C. And so that's going to be 1 over J times 100 times 5 milli, which is negative J over 0.5, which is negative 2J, negative J2.
That's it. So we've got a negative J2. And let's finish drawing this in. So this is J3, we said. Here is our dependent source. I'm going to draw it in capital letters now since we're in the phasor domain. And we've got this capacitor here that is minus J2. And at this point, I'd say, what's the small? We need to fill in all of our variables. So we've got our I1, which is now going to be drawn capitalized. And at this point, I would say, what's the smartest way to solve it? Can we solve it using simplification? Could I take a source transform of these two guys? Liam, can you do a source transform without destroying anything that you need to find for what I just drew in red? I don't want you to jump to a solution method and say, this is how I'm going to solve it. I want you to look at all possible solution methods and come to a smart one. Right now, it's not.
I think you wouldn't destroy anything. I think that
You're
would
correct.
be okay. But I also don't see the reason to do that, you know?
Well, so here's the problem. Things are neither all in series or all in parallel. So if we could source transform this, everything to the right of this would become all in parallel. Meanwhile, if we source if we source transformed this too, then we'd have a pure parallel circuit and we'd be done. We could just use a simple current divider relationship and walk away. So is that allowable? Can we source transform the left?
You can't, because that would destroy I1, wouldn't it?
So that's an interesting thing. Watch this. If we were to source transform to the left of this, it might seem like it would destroy your I1, but look at this. Your I1 actually exists outside that. Agreed?
Yeah, but doesn't it also exist within that?
It does. And the I1 that exists inside it would be totally destroyed. But the I1 that's outside it does not get destroyed. And so since that's the same as the I1 in here, even though after we transform it, none of the internal voltages and currents we can consider will be the same as in this. Everything outside has to stay the same if our transform means anything. So therefore we could. And with two source transforms, we'd magically change this into something that everything is in parallel, and we could solve it with a current divider. So that's one way that you could do it. I'm going to keep you in the hot seat for a little bit longer, though. And I'm going to ask you, let's come up with another way. Could we come up with a source transform that makes everything in series? Is there some way that I could say source transform this with anything to make everything in series?
I mean, I think the closest you could do would be with the 3I1, but I don't really see a reason to do that. But I think, okay.
Yeah, that's the question is, could I source transform this to make everything in series? Everybody listen to this because this is a very critical question.
I don't think so, because 3I1 is a voltage source.
The reason why you can't source transform is because how many wires come out of this transform? Three. You don't know anything, any source transforms that have 3 wires coming out of it. So the answer is no. So that won't work. So far we have one way we could source transform left and right to make everything in parallel, make it into a big current divider equation. We could do a superposition. That's not really going to help us if we did a superposition, because we can't take out the dependent source in the superposition. So we're left with what we started with. Could we do nodal? How many unknown nodes do we have if we do nodal? Let's say our ground is on the bottom. That's a reasonable place to put it.
Well, then that would be known. So I guess 3.
Well, let's see. This is a known node, right? This would be 10 square root of 2.
That's known.
And an angle of 45.
In the middle.
We don't know this one. So that would be V1. What's this guy over here?
2.
Nope, not even 2. What's this guy? You know what this voltage is? Here's another voltage source.
That's V1 minus 3I1.
Minus 3I1. So if you did a nodal analysis, you'd only have one unknown node. And then you'd have to come up with an extra equation because you've got this dependent source. You'd end up with a 2x2 set of equations. That's not too bad. Unfortunately, you'd end up solving for V1, from which this would be pretty trivial. And that's not the same as finding I1. So while you only have one equation unknown with nodal analysis, not necessarily the best because you end up solving for voltages. So instead, let's do it for meshes. And with meshes, how many unknown meshes do you have?
Just 2. Right?
Just 2. And I'll kind of arbitrarily draw this one in this direction. That seems worse than nodal, because with nodal we only had 1. But remember, in nodal you had an extra equation because we have this dependent source, whereas in mesh, this extra equation is already part of it. We already have what I1 is. So it's the same work as nodal. The only difference is with mesh, we're directly solving for I1 and I2 in one step. So that seems to be the smarter approach. It didn't take that long to look at all the different ways to solve this thing. Do that with every problem you take, because if you choose the wrong way, you might end up with a much more complicated problem than you need to. All right, so KC, we'll start to do mesh. Let's do it around I sub 1. We're not saying I1 is equal to this. We're just saying we're going to do it around I sub 1. So let's start it off with up here. What's this guy?
So I1 would be, so you could do
We go into the negative side. So that's
negative 10 squared or 2 squared or squared
negative
2.
10 squared to 2.
Yeah.
At that angle.
45 plus I1 of 3, right?
Plus 3 times I1, yeah. So we are adding voltages, and this is a voltage, and resistance times a current is a voltage, and then we're going to go down here. Yeah, so this is going to be J3. And then my question for you, KC, is how much current do we have going down it? From this side, we've got I1. And how much current is going down it from I2?
Would it be minus I2?
That's it.
Yeah.
And that's the whole circle. That's the whole mesh. And so all that has to be equal to 0. And now let's get it into our standard format where we've got unknowns on the left and knowns on the right. I'll do that. How much, the question is firstly, how much I1 do we have? And we've got 3 from this, and we've got J3 from this, and that adds up all of our I1. And Cole, I'm going to call on you next to do the next mesh. And how much I2 do we have? We've got just minus J3. And then we put all of our constants on the right side. So that would be equal to 10 square root of 2 angle of 45. And now we can do it around mesh 2. So Cole, tell me where that begins. Let's start it down here going up.
Where would you like to start, sir? Sorry.
Let's start it from the J3.
All right, J3, I have J3 parenthesis I2 minus I1.
That's right.
And then I have plus 3 parenthesis 10 radical 2 angle 45 divided by 3.
Oh, that is not correct, but that's an interesting idea. So what you've done is it's really, you're going around and it's really, you're entering this guy. So it's really 3I1, right? This is the voltage.
J2.
Minus what?
J2.
Minus J2. I'm sorry, I misheard you. I thought you were solving for I1 right there. Yeah, no, that's exactly
what I did. But
so did you initially say something with I1 involving 10 square root of 2, or did I just mishear you?
No, I did. I said I1 was 10 radical 2.
All right.
Angle
So
45.
What Cole did, which is not correct, but it's close, is he was going to solve for what I1 is. And he looked over here and he said, well, there's a 10 square root of 245 degrees on this side of the voltage source between here and here. So therefore that must be the voltage across this resistor. And so therefore I1 has to be equal to that voltage source divided by 3. But that's not right, because just because there's this voltage between these 2 points doesn't mean there's that voltage across the resistor. Just because you know what the voltage is between points A and B, between bottom and top here, doesn't mean that you know the voltage across this resistor. In fact, the voltage across this resistor will be different than this as long as there's any voltage at all dropped along J3. So let's write this in terms of unknowns on the left. We've got how much I1 according to this. Let's see, we've got 3 from this, and we've got minus J3 from this. How much I2 do we have? Just J3. And then we put our constants on the right. Ooh, I made a mistake. As we're summing voltages, we got the voltage here correct. We got the voltage here correct. The voltage here is minus J2 times I2. So let's update how much I2 we have here to say we've got our plus J3 from here, minus our J2 from here, plus J3 minus J2. And I'm just going to write that as just J. And there's no constants at all here. So now we can write our matrix. And our matrix will be using this thing. We'll have, these are our 4 matrix components. So it's 3 plus J3 minus J3, 3 minus J3, and J. And all that is times your I1, I2. And that equals what you've got on the right side of the equation, 10 square root of 2, angle of 45, and 0. So you put that in your calculator and out pops I1 and I2. And if your calculator is in degrees mode, complex polar notation, it's going to say it's equal to 1.05 at an angle of 71.6. I don't care what it says down here because all the question asks for is what is I1? And so now you can write the answer. Let's see, Ben Wallace, tell me, what is I1 of T?
Would be 1.05 and then cosine of 100t plus 71.6 degrees.
That's it. Don't forget that last step to send it back into the time domain. All that we're doing with phasors is just a convenient mathematical shorthand to figure this out. But at the end of the day, you've got to convert it back into the real world, into the time domain world. And that's it.